Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1,000th of a gram. Excess or shortage means danger for the shooter and weapon. A 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. but installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast's force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture. Imagine a river of white-hot metal as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the US, just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, two other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gas is rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light, molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of 2 unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron, and floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the U.S. produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.